Could we build an electromagnetic mass driver to launch payloads in space? Could brown dwarfs be dark matter? And does humanity have the ability to see an Earth-sized world orbiting a sun-like star in the habitable zone? All this and more in this week's question show. It's time for the question show. Your questions, my answers. Now, as always, wherever you are across my channel, if a question pops into your brain, just write it down. I'll gather them up and I will answer them here. Now, before I get into this week's question show, I just want to remind you, I say this at the end of every episode, but I say at the beginning of today's episode, I write a newsletter, an email newsletter. It is thousands of words long. It contains dozens of stories about space astronomy, really cool pictures for each one of the stories. Not a lot of words, like a number of words that you could skim really quickly while you're reading your email on your phone. And it is what I would want to read if I was receiving an email newsletter, and it is like a distillation of every single news story that I have seen in this entire week. So if you want like the most comprehensive email resource, a newsletter for space and astronomy that you can imagine, I guarantee it is my newsletter. Go to universetoday.com/newsletter. Now, we record this show live every Monday at 5 p.m. Pacific time. So if you want to come and join the live show, ask your questions, do that. Come to the channel at 5 p.m. Pacific every Monday. Now, don't forget about daylight savings time. It completely caught me by surprise this week. So, don't be me, and just make sure that you remember that all the clocks have been sent through a time traveling device. All right, let's get into the questions. Simon Jennings, we can fire objects at crazy speeds on Earth using magnets, but in a vacuum, the speeds become crazy. Is there any way we could construct a giant electromagnetic tunnel in space and use it as a launch tube? Thank you for all your content. I love it. Theoretically, yeah. Now, the technical term for this is a mass driver or an electromagnetic mass driver. And what you're using is this very simple, very long known sort of trick of electricity, is that if you run electricity in a coil, it creates a force that runs in one direction perpendicular to the coil. And you probably learned this like in your high school physics class, where you are running electricity through a wire, you coil the wire, and all kinds of really cool things happen. You get magnets and you get a force. It's how motors work. Like, we know this aspect quite well. And we've known as well for decades that you can use this force to accelerate mass. And the idea is, like, imagine you've got this coil, and then in the middle of the coil, you put in some kind of mass in a capsule. And then because of this force that's being applied to it, the capsule is being accelerated along this coil. And if the coil goes long enough, the capsule gets faster and faster and faster. And then right at the very end, when you're just about to launch your projectile, you detach the capsule, the payload is inside, and away it goes at very high speeds. And we're talking really high speeds. Like, there have been electromagnetic railguns that have been run at hundreds of meters a second, thousands of meters a second. You can get very fast with this technology. And back in the 1970s, the L5 Society, this is like Gerard K. O'Neill, who imagined these giant rotating cylinders at the Earth's moon L4 and L5 locations, wanted to build these gigantic habitats, but they needed a lot of material. And they're like, where are we going to get this stuff from? And so their thought was, well, if we bring everything up from the moon, then we'll have enough raw material, the regolith coming from the moon. And so he proposed that they build these electromagnetic railguns on the moon. They then scoop up regolith into blobs, fire them down on this railgun, and then they would be accelerated beyond the escape velocity of the moon. They would go up to, say, the L5 Lagrange point, or maybe they could go to the Earth-Moon L2 Lagrange point, which is the one that's on the far side of the moon. And then from there, you could get out to the rest of the solar system. So there's a lot of value. And according to their math, and this is their math, they figured they could get the launch costs down to about $1 a pound. and they could deliver hundreds of thousands of tons of regolith and other minerals off the surface of the moon to the L5 point, fuel to build these gigantic rotating space colonies. But they took this idea and thought about what would happen here on Earth. Could you build an electromagnetic railgun that could actually launch payloads off of the Earth? And they did the math, and if you built a tube that went down into the Earth that was, say, about 10 kilometers deep, longer, you could launch a telephone pole into space. It wouldn't be an actual telephone pole. It would be a sharpened metal tube, a rocket, and you would be able to just generate the electricity. You would accelerate this payload up to the top of the tube, and then it would fly off into space. It would definitely hit the wall of atmosphere, but it would still only lose some of its heat shield as it goes up. It would lose about 20% of its speed as it went up, and it would be able to get out to escape velocity. The only downside is you would need about 76 gigajoules of energy that you would have to sort of bring in from the surroundings, concentrate in the small area, and then apply it to this electromagnetic railgun. But theoretically, all of this is true. It would work great on the moon. It would work even better off of asteroids. So you wanted to mine an asteroid, you would just attach one of these railguns, and they wouldn't have to be very big. And you could start accelerating material off the asteroid into space and fire it on some kind of trajectory that would either take it to the L5 colonies or to Earth, where it would re-enter the Earth's atmosphere, and we would all become fabulously wealthy on all the space gold. And now you're like, why isn't this happening? Because it's incredibly expensive to build. Like, it's an enormous amount of infrastructure. And the bottom line is that we don't need it. That the amount of material that it would take to build this infrastructure, compared to the amount that we would be able to harvest, compared to the amount that we use here on Earth, that would go above and beyond what we can find just by digging holes in the ground, it's just not worth it. It's just not feasible. And so only when we get to a point where we have a thriving solar system spanning civilization, as we are starting to build things in space, like these giant O'Neill cylinders, will we need to be bringing large amounts of material from these asteroids, the moon, etc. And like, the joke that we always make is that the best way to lose $1 million is to start an asteroid mining company. There is a graveyard filled with companies that have attempted to begin asteroid mining, and that's because there is just no market for it yet. Why build this very complicated and expensive asteroid mining company and system and all this technology when you can dig a hole in the ground and get what you need right now for a fraction of the price? So the science is solid. It is an engineering problem that is eminently solvable. That if we wanted to, we could absolutely be running giant electromagnetic mass drivers off of the moon or asteroids. It's just that we don't want to yet. And when the economics of it changes, then we will. Now, you've probably noticed the Star Wars planet above my shoulder, and now that The Mandalorian is back on, I guess it's time to get back into the Star Wars planet mood. This is actually a way that you could vote for the question that you thought was the best, and a way to give me some kind of feedback on what we're doing a good job of, what kinds of questions you really like to see. So it's very valuable to me. So please vote. All you got to do is just go down into the comments down below and just type in the name of the Star Wars planet that you like the question to the best. And then we will gather up all those votes and we will celebrate the winner. So last week, Farmer John asked if the Earth had enough internal energy to steer the Earth clear of the sun, and you liked that question, that answer. And so congratulations, Farmer John. Congratulations to me. We made a good team. So once again, go ahead, vote for this week's question down in the comments down below. All right, let's continue. Eli Vyas. I believe you said it's very hard to estimate the number of red dwarfs and brown dwarfs within 100 light years of Earth. Have red dwarfs and brown dwarfs been ruled out as a source of dark matter? And if so, how? Why? Thanks. Yeah, so the idea of dark matter has been around since the 1930s, when astronomers first started to calculate the rotation curves of galaxies, and they realized that the galaxies are rotating so quickly that they should pull themselves apart. They should just break into pieces and fly off in many directions in space. There is the mass of the stars and the dust that we can see in the galaxy, and then there is some additional mass that is like glue that's holding the whole galaxy together. And the ratio of that is about 6-to-1. So there is much more dark matter than there is matter. And that's the only way that you can get these galaxies to hold themselves together. And so once astronomers started to notice that, that there was this missing matter that they couldn't make sense of, the question was, what is it? And then they had a bunch of ideas. They're like, well, maybe it's missing gas. Maybe it's dust and gas that we just can't see. Maybe it is stars, brown dwarfs, red dwarfs that are just too dim and we can't find them. Maybe it's black holes. Maybe it's some particle that we don't understand. Maybe we don't understand gravity at the largest scale. So many different ideas for what dark matter could be. And then they went about testing each one of these ideas. And so this idea that maybe it's brown dwarfs and red dwarfs. So we know, based on the cosmic microwave background radiation, that at the beginning of the universe should be hydrogen and helium. Like that was there, that was at the beginning. And so we should still see those ratios roughly today. And we do. When we look around the galaxy, we see hydrogen, helium, we see clouds of hydrogen and helium that are going to form stars. But if there was a hidden population of stars that were many times more than the population of the regular stars that we can see, the gas and dust that we can see, then it would be the brightest thing in the galaxies themselves. Even though each individual one of these objects is fairly dim, if you add up all of it, they would be very bright. The second thing is that astronomers have done surveys for the number of brown dwarfs and red dwarfs that are in our environment. They've used very powerful telescopes like WISE to do this detection, and they were able to calculate the number of them that are out there just in our vicinity. So they find that there's a ratio of about 4 regular stars and 1 brown dwarf. And most of those regular stars are red dwarfs. And so based on the number of stars that they found in our vicinity, if you sort of extrapolate that, it just doesn't add up enough to be dark matter. But I love that process, right? You think of a thing and you go, could that be dark matter? Right? You discover a fact. There are these failed stars. You have a hypothesis. Could they explain dark matter? You do an experiment, you build a multi-million-dollar space telescope and you launch it and you survey the nearby surroundings for brown dwarfs to calculate and estimate the amount that there are in the galaxy. The number comes back and says no. And so you have disproved your hypothesis that brown dwarfs could be dark matter. You did science. And I think that's great. Can't be serious. Does humanity have a telescope powerful enough to see an Earth-sized planet orbiting a sun-like star in the habitable zone? If so, has anyone discussed creating such a telescope to look at sun-like stars for year-long intervals? No. We do not have the capability today to observe an Earth-sized world orbiting a sun-like star. We don't have the ability to observe it using the radial velocity method, where you measure the back and forth movement of a star based on the gravity of the planet that's orbiting around it. We probably have the capability with the transit method to watch as the light of the star dims as a planet passes in front of it. And we do not have the ability to observe it directly the way we've observed other exoplanets directly. And this is a thorn in the side of astronomers. Anyone who has been studying exoplanets, the thing they would most like to see is an Earth-sized world orbiting a sun-like star inside the habitable zone. We found Earth-sized worlds orbiting non-sun-like stars in the habitable zone. We found Earth-sized worlds outside of the habitable zone, but we haven't found that Earth 2.0. But as with the last question I said, right? Hypothesis. There should be Earth-sized worlds orbiting within the habitable zones of other sun-like stars because Earth is one of them. So maybe there are others. So then you perform an experiment. And in this case, the experiment that you perform is you build a multi-billion-dollar telescope designed for this very job, as well as other jobs. And so there is a few telescopes in the works that are going to give us this data. The one that's most likely is the European Southern Observatory's extremely large telescope, the EELT. And this is going to be a 39-meter telescope that's being built in South America. So like when you think about like the biggest telescopes on Earth right now are about 10 meters across. Like most are 8 meters. There's one that's 10 meters across. You can combine the light from 4 different 8-meter telescopes to make a virtual telescope that's bigger. But this is one telescope that will be almost 40 meters across. It's a ludicrously big telescope. Oh, that should have been the name. Anyway, it's the extremely large telescope. We'll save that, I guess, for a future telescope. And it will have a coronagraph. And this is the key to the whole technology. You need to have a coronagraph. Coronagraph is a device that sits on the telescope and blocks the light from the star, because the light of the planets are like 1 billion times less bright than the light from the star itself. You block the light from the star, and now you can see the planets that are nearby. And so the extremely large telescope is going to have these two things. It's going to have a coronagraph that is capable of blocking the light of the stars, and it will be big enough to be able to see and resolve the existence of these planets. But you're not going to get like a really cool picture of an Earth-sized world with mountains and forests and clouds and all that. You're going to get a dot, 1 pixel. And that's it. Now, there are other space telescopes that are in the works. There's one that was proposed called HABEX, and it's probably going to get merged into LUVOIR. So you're going to have this thing called LUVEX, and it will be a space telescope that'll be around the size of JWST, but it will also have a space-based coronagraph that flies far away from it that will just float in front of the star and block the light. And then the space telescope will be able to observe the planets that are around it. And that will be the same thing. It will allow us to see these Earth-sized worlds orbiting around sun-like stars. And again, this is the Holy Grail. So at the time that we're recording this, we are about 3 years away from the extremely large telescope. LUVEX, whatever it's going to be called, will probably launch in the 2030s. And then the most exciting idea is called the solar gravitational lens. And this is where you fly a spacecraft out to about 1,000 astronomical units away from the sun, a place where the gravity of the sun acts like a natural telescope lens. And you can fly down the focal point of this gravitational lens from the sun and use it to observe one target. So one exoplanet that you really want to see. And from that, you would be able to see an image of a planet that's about 1 megapixel. So 1,000 pixels by 1,000 pixels. And in that picture, you would see mountains and forests and oceans and clouds and maybe even the presence of life on that planet. So it will be a ladder. We will complete the extremely large telescope and start to detect the existence and maybe try to characterize the atmospheres of these exoplanets. Then HABEX will come online, find more planets, and do even better observations. And when we're absolutely sure that we figured out our target, we will start sending out these spacecraft to the solar gravitational lens to do the best analysis we can possibly do. If you like my answers to your questions, as well as the other things we do at Universe Today, consider joining our Patreon club. This allows us to keep the minimum ads for everybody. Like, as you can see, there are no ads in the middle of this video. Thanks, patrons. Now, as a patron, you get an ad-free experience on Universe Today for life, even if you unsubscribe. You get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. And thanks to everyone who has already subscribed, and welcome to our recent newcomers: Mike Kroll, Jeff Lewis, Doreen Balbuena, David Faulkner, Sesh Gremlin 117, Terry Sullivan, Nick Hansen, James Hapgood, insert witty name here, Leon Haas. Join the club at patreon.com/universetoday. Rev Keith Carter, is there a website that shows the programs that JWST will be working on, and can you share it with us? Yeah, absolutely. You can see a list of all of the targets that JWST is expected to be looking at this week. And then you can see all of the targets that it looked at in past weeks. So all you got to do, you can go to the Space Telescope Science Institute's observing schedule for JWST. Do a search on Google for JWST observing schedule and you'll get it. And what you get is a list of all of the targets that it was observing week after week from the beginning to now. And when you look at it right now, I'm seeing about 40 maybe weeks that it has been observing so far, and it shows the current week. So at the time that I'm recording this, it says March 13th to March 20th. And then you can click on the observing schedule and you can see all of the targets hour by hour, day by day, the duration, which instruments are being used, and what it is. And like, I'm going to warn you, like, if you look at this, like, you're going to learn too much about what's coming down the pike and you're going to be too excited. And now you're going to have to wait for this stuff to actually show up. So for example, I'm looking at the schedule that we have this week, and there's going to be an imaging of the Crab Nebula, which is one of the most beautiful and famous objects in the night sky. You can see it in a small telescope. We've seen pictures with the Hubble Space Telescope and other telescopes. JWST is going to take an image of the Crab Nebula. Yes, please. We've got upcoming observations of Beta Pictoris, and it is known to have planets orbiting around it. And it's going to be using the coronagraph to block the light from the star to try and reveal objects around Beta Pictoris. So maybe we'll get some direct images of planets orbiting around Beta Pictoris. And more, like, there's some galaxies here. I've got to sort of do some searches to know which these galaxies are. But the point is that there are some pretty exciting targets that have already been planned out and data has already been gathered. But now it goes to the astronomers. The astronomers have to write their research, and then this gets released to the public. So we could be months away from actually seeing the science that's coming from this. So as I said, this is a very dangerous list to go and look at, because it'll just make you hope, and it'll be like waiting for Christmas and you can't sleep. Moonwalker. How much more energy does it take to launch something in Nova Scotia versus the equator? Now, if you were here for the live show, this is sort of a follow-on question to a question that I answered about whether or not we were going to have launch facilities in Canada, but I don't think the original question is going to make it onto the question, so now I'm giving you a quick version. But so Canada is building a spaceport in Nova Scotia, and that seems crazy, right? You know, we know that spaceports are built as close as possible to the equator, and we actually last week talked about this idea that if you are on the equator, you get to take advantage of the Earth's rotation, which is about 1,650 kilometers per hour as additional velocity you get to add to your rocket, or it lets you reduce the propellant that you need to be able to reach your orbit. So there's lots of real advantages to put your launch facility near the equator. But that only matters if the orbit that you want is equatorial. If you want to launch something and you don't really care where it goes, you just need it in space, then you launch from the equator. Or if you want to fire something out along the plane of the ecliptic, you want to go to Mars, you want to go to Jupiter, then you launch from the equator. But there are other orbits that have value as well. And one of the other most valuable orbits is what's known as a polar orbit. And so instead of your satellite going around the equator, you follow from pole to pole, from above the planet to below the planet. And what this gets you is you launch your satellite and now you're in orbit around the Earth from pole to pole, but the Earth is turning underneath the orbit of your satellite. And so over the course of each orbit, you're sweeping a different part of the planet, and your spacecraft is capable of seeing every single part of planet Earth. And for certain Earth observing satellites, for if you're gathering data about planet Earth, there's real value to doing a polar orbit. And then being at the equator doesn't matter. It doesn't help you, because you don't want that speed boost going sideways. You need to be able to go north-south, south-north. And so Canada is as good a place as any to put a launch facility that can launch on a polar orbit. What is the difference of fuel? Well, you don't get that advantage of being at the equator. And so polar orbits are more expensive in terms of energy of propellant to put a spacecraft into orbit of the same payload than if you're going to launch it into an equatorial orbit from near the equator. Steve Lenoris, will China own the moon? Well, according to the Outer Space Treaty of 1967, nobody can own the moon. Space is for all mankind. And so it is the common resource of all humanity, in the same way that nobody owns Antarctica. You can't go and claim a chunk of Antarctica and say that it's yours. All of the signatories of the Antarctic Treaty will not permit it. And the same thing goes with outer space. So nobody can own anything in space ever. Can't own Alpha Centauri. You can't own Titan. You can't own any of that. Now, you can go to these places and you can set up a research station. And in some really edge cases, you can go to these places and you can set up a in situ mining operation so that you can support the needs of your research station. But if anybody, if any nation on Earth said, we're going to go and own this part of the moon or own that asteroid, every other nation on Earth would say that's a violation of the Outer Space Treaty. So no. And because these nations are still down here on Earth and they have to interact with each other on a day-to-day basis with trade and so on, you can imagine them getting, there being embargoes. And so if you were like, I can't even imagine this, right? Like China would go, we own the moon. And every other nation on Earth would go, no, you don't. And we'll stop buying your stuff until you change your position on this. And then China or America, anybody says, no. And then they go bankrupt and they have their economies tank and there's no value in the moon, right? There's no money to be made on the moon. And so you have tanked your economy for no reason whatsoever. So I think we can safely say that there's no reason that anybody will claim any property on the moon for the foreseeable future because there's no value there. And it's like the same reason why all of these countries were willing to sign the Antarctic Treaty, because it's so hostile, so remote, so difficult to extract resources from this place that it's not worth fighting over. So like, just don't fight. And it's the same thing for space. And like, I know people are fear-mongering this, but it's crazy to think that. So when will you go, wait a minute, we might have a problem here? You would have a problem, and you can sort of look to history when we had problems, when you had, say, colonist nations like the United States separate. First they were self-sufficient, then they separated. So you can look at the United States of America, like first it became self-sufficient from Britain, then it separated. And so you would need that same chain of events. There would need to be a thriving society on the moon, a thriving society on Mars. And then that society, completely self-sufficient, no longer requiring resources to come from planet Earth, or maybe they had an alliance with one country and that country was willing to take the risks with all of the other countries on Earth. They would say, we are independent. We own ourselves. And then other nations would decide whether they were going to go and try and stop them, whether they would send a military blockade, whether they would try to invade them. Like, I don't get it. So I wish I could get across just how little value there is out in space to human beings today. That, we mentioned this earlier in the show, that setting up asteroid mining companies is one of the best ways to lose money. That there's no value in space power. There's no value in all this stuff. Right now, the only value that space has is how it can help us do our jobs better here on Earth with communications, with navigation systems, things like that. And science, in us doing research, understanding the universe better. That's the value. And if we saw some kind of economic engine start to get going in space, then you may want to change the calculus. But we are so far away from that. So no, I think, like, what are the Chinese going to do? They're going to send human beings to the moon in the next decade or so, and they're going to walk around on the moon, and they're going to set up a research base, and they're going to demonstrate to the world that they are a world power, and that only a nation capable of sending humans to the moon has that level of capability and power and should be treated with the respect that they believe they deserve. It's hard to, we can decide whether we're impressed by people sending humans to the moon. Each one of us, each nation can decide for themselves what that means. But that is the message that they're sending, is that they are ascending to the top of the power ladder to be able to do this. It's a power move. They're signaling, and we can decide what that means. But there's no money to be made on harvesting resources from the moon. No reason to own it. Only downside because you're actually down here on Earth. Big Mike, should SpaceX just be the only launch service for the USA so they can save money? Like, should some company be granted a monopoly? No, never, never, never. No monopolies. Their monopolies are bad for consumers, for the economy, for business, everything. So no, I mean, like I know people like to dunk on other launch companies, but you should be excited by any launch provider that is putting their hat into the ring, like Blue Origin, like United Launch Alliance, like Relativity Space, what they're doing with Spin Launch, and a lot of other, other countries. The fact that they're setting up launch services in Japan, and even what China's doing. That a vibrant economy requires a lot of players and requires competition to bring prices down. And so no, I mean, if you just had one launch provider, then they would have a monopoly, and then they would use that monopoly to exert control and raise prices and decide how we get to space. I mean, like, we make fun of Boeing for the Starliner and the delays that have happened. I mean, at this point, Starliner still hasn't launched one time, while Crew Dragon has launched 7 times and is accelerating its launches. But you want Starliner to succeed. You want there to be 2 viable ways that the United States can send astronauts to the International Space Station. And then you want Dream Chaser to be sending cargo to the space station. Like you want as many options for us to get into space as possible. And I don't think it ever makes sense to just cede control to any one company and let them have a monopoly. Serdar, what would you ask an alien if you meet one as a science reporter? Like, that would be the interview of a lifetime, wouldn't it? to interview an alien. I mean, we here on Earth have only one example of life and all of the different forms that it's taken, but we don't know of anything beyond Earth. And so there are all of these things that we take for granted. And so my interview with an alien would kind of be similar. Like, have you ever gone to another country and met a local, and most of the time you're asking, like, what do you guys like to watch on TV? And what music are you into? And what kind of food do you like to eat? And you're trying to find out, is life for you similar or different to how it is the life for me? It would be that, but just like times 1,000. Can you imagine the kinds of like things that we take for granted in our life today? You would ask an alien. You'd be like, how do you reproduce? How did you guys develop language? What is your relationship with the natural environment? How does your society break? Like there would just, like, you would literally take every single piece of human knowledge and you would want to compare and contrast with their experience. Did you guys figure out that, how electromagnetism works? Did you realize that large language models are a good way to develop artificial intelligence? Did you, like, all of these scientific discoveries we made? And we'd want to ask them about ones that maybe they had figured out that we hadn't figured out yet. Yeah, I would be relentless. Please, if there are any aliens out there who would like to be interviewed, I'm your guy. Music cassette. Could a balloon on Venus use the temperature differences in the atmosphere for power? I've been doing a series of interviews about Venus, and that's because I'm kind of obsessed with Venus right now. I've interviewed about landers on Venus, about interesting new ideas for missions, but also Venus's habitability and how it compares to exoplanets. So you've seen a theme. I'm obsessed. I'm sorry, you're just gonna have to let me work through this. So there will probably be more interviews about Venus coming. I saw like a paper today, and I'm like, ooh, I want to interview that person. They were sort of figuring out when Venus lost its water, and I want to interview them. But anyway, so after the interview, we got a lot of comments in the chat about people asking, like, Venus is so hot and steam turbines are hot on Earth. Couldn't we use that high temperature to run power? And the problem is that you need a temperature differential. So if everything is the same temperature, then you can't exploit the difference in temperature to do work. A steam turbine only works because you're taking cool liquid water, you are then heating it up to create steam. You're then extracting the steam, and that's providing you the energy. And then or to do work. And so you're using some power source to heat up the water, you're extracting the steam, and then you're doing work. And you would need to have that temperature differential, and everything's the same temperature, then it wouldn't work. Yeah, when you land a spacecraft, the inside is going to be cold and the outside is going to be hot, but the hot temperature is going to work its way in and bring up the temperature to be the same. And so you just can't do work. But if you could find a temperature differential, then maybe you could exploit that to do work. And we do that all the time here. Like here in my house, I have an air water heat pump. So I have a heat pump that sits outside my house, and it runs, it utilizes a difference in temperature between the inside of my house and the outside, and it's able to extract heat and to be able to warm up my floors. And it's very cool technology. They're very efficient, relatively inexpensive compared to other ways of heating your home, and they take advantage of this temperature differential. So if you're on Venus and you want to take advantage of a temperature differential, there's a couple of places you can go. One is down into the ground. And so, which would probably be pretty tricky, because we know that on Earth, yes, the temperature at just below the ground on Earth is often very cool, just a couple of degrees. And then as you go deeper and deeper, it warms up. But that's because the temperature at the surface can be freezing. But on Venus, the temperature is 460 degrees. So it's going to be hot on the surface, hot under the ground. And then as you go deeper, it's going to get hotter and hotter and hotter as you get closer to the core of Venus. So what about going up? Well, we know that the high altitude of Venus, when you're above, say, 75 kilometers altitude, the temperature is like Earth and the pressure is like Earth. And if you go higher still, then the temperatures continue to go down until you're far below zero. And so theoretically, you could exploit that temperature differential on Venus to be able to do work. But like from an engineering standpoint, I can't imagine what that machine would look like. Like a tether that is 75 kilometers from a balloon down to some rover, and you're pumping cold fluid down the tether down to the rover to keep it cool inside, or to run a wire down to the rover where you're giving it electricity so that it can keep its cooling system rolling. I don't know what it would take. So theoretically, yes. Practically, I can't imagine how, but I'm sure somebody has thought of this. All right, those are all the questions that we had this week. Thank you, everyone who asked questions in the chat, and thanks to everybody who showed up for the live show. Remember, we record this show every Monday at 5 p.m. Pacific time, so come hang out, join the show, ask your questions live, follow-up questions. It's a lot of fun. Now, don't forget to vote. Put in the planet name for the question that you thought was the best. See you next week. If you want to stay on top of all the important space news, join my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universe.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast, or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the Galaxy Wanderers. And a special thanks to David Giltonen, Modso, George, Jeremy Matter, Jordan Young, Tim Whalen, Dave Verabioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.